Okay, in this video, we're going to look primarily at the synthesis and reactions of epoxides, the most reactive of all ethers. Okay, so we've already had some methods to synthesize epoxides. The most important one probably would be from alkenes. Okay, if you recall from in the first half of the course, if you treat an alkene with this type of compound, peroxy acid, notice how there's three oxygens right here. That's a peroxy acid. If it's just two oxygens, of course, it's a carboxylic acid. Okay, so this has an extra oxygen relative to a carboxylic acid. Okay, so what happens there is you get a syn addition and you get an epoxide. Whatever stereochemistry you had for the alkene, it ends up being in the product. So right here we have a transalkene. So we're going to have a trans arrangement of our two substituents, R1 and R2, are trans on the three-membered ring. Okay, in addition to the peroxy acid-based synthesis, we also have a two-step alternative where we use this reaction that you may recall from the alkene chapter, where we treat it with halogen and water. This is called halohydrin formation. Okay, this process adds an X group and an OH group. There's some regiochemistry that goes along with this, but we're going to see that that doesn't matter because we're going to get rid of the regiochemistry in the next step. All right, so we treat this with a base under as mild a conditions as we can, and this will cause the halohydrin right here to convert to the epoxide. All right, the overall result is the same as in the top one. Okay, it's a syn addition, but it's a syn addition for a different reason. This is because step 1 is an anti-addition, and step 2 is an SN2 reaction, which goes with inversion of configuration. So when we think anti and inversion, we see that we have two basic things that invert the stereochemistry, right? So we get the net syn addition because we have an anti-addition followed by an SN2 rearrangement going with inversion. So we can say that the syn addition is kind of like saying that two wrongs are making a right. Okay? This latter SN2 reaction is usually very successful, okay? Regardless of our substitution pattern here, and this is because this tends to be a very good reaction. If you look at the trajectory that you need to do an SN2, which is completely from the side opposite your leaving group, you find that your oxygen is almost in the perfect place to do that process. So that's why we have such a good SN2 reaction here, even though we're making a three-membered ring, and three-membered rings we've long known have a lot of angle strain. This one actually proceeds quite readily because the oxygen is just lined up in the right place for an SN2 reaction. Okay, what happens when we have an epoxide? Okay, we have two types of ring opening, which you may have seen at the end of the video. Let's look at the most important of these. This is nucleophilic ring opening, or base catalyzed or base induced ring opening. And so we're going to use this compound here as an example. This is because it's cyclic and it's very easy to see the stereochemistry in a cyclic reaction, and because it's unsymmetrical. If we treat this compound with a variety of nucleophiles, what we're going to see is that our nucleophile does an SN2 reaction, and we can write it like that. Okay, after protonation of the alkoxide intermediate, we're going to end up with this type of compound, and notice that our nucleophile group and our OH group are ending up in the trans orientation here. And this is because if we look here, this CO bond is not affected by anything that's going on in this reaction, right? So our nucleophile is attacking this carbon. We're keeping the same stereochemistry at this place, but we're inverting the stereochemistry here. So here we see an inversion because that's where the SN2 is occurring. And where I have the asterisk, we're seeing retention. That's because nothing is really happening to that CO bond. Okay? Now, why does it go here? This drawing is getting a little bit crowded, sorry. This is because this carbon is secondary. This carbon is tertiary. And what do we remember about the SN2 reaction? Okay? The SN2 favors methyl greater than primary, greater than secondary, much better than tertiary. Okay, so the nucleophilic or base-induced epoxide ring opening is purely an SN2 mechanism. We attach our nucleophile to the less substituted carbon of the epoxide, and it comes from the back side. The net result is inversion at the carbon where the CO breaks and retention at the CO bond where the nucleophile doesn't attack. Okay, so let's look at a series of nucleophilic epoxide ring openings. All of these involve reagents you've seen before. Here our nucleophile is H-, right? Remember that hydride is a source of nucleophile minus, so we're going to see the reaction occur right there. And the product of this reaction is the alcohol. The new hydrogen that we added is technically right there. Remember, we had 2 hydrogens when we started. We have 3 hydrogens after the reaction is over. Okay, here we have a Grignard. A Grignard reagent is a good nucleophile for opening an epoxide, and we're going to attack here because that's the less substituted side of that or less substituted carbon of that epoxide, and the product we're going to end up with is the one shown here. Okay, here we have the methoxide. Sorry, no, yeah, all right, sorry, the ethyl group added to the epoxide. There's our ethyl right there, and ends up producing the compound shown here. And again, the carbon I have drawn the arrow to is primary, that carbon is secondary, so we're going to attack the primary carbon. In this next one, sodium methoxide is the nucleophile, so we're going to add OMe- to the system. Okay, and again, this is just like the one at the top. That side's secondary. This side is tertiary. We're going to see the SN2 prefer the secondary over the tertiary, and this is the product that we would expect. Okay, and this last one is going to be a little bit harder because both sides are secondary. This is secondary and benzylic. This carbon is just secondary. So remember that benzylic systems are actually activated for the SN2 reaction as well. So these are nucleophiles that you saw in the nucleophile chapter. Every one of them is going to add from the to the benzylic carbon, and it's going to add in such a way that we get inversion at that carbon, and the OH group is going to end up at the other carbon, and the stereochemistry there is not going to change. All right, so here are the products from the various nucleophiles attacking this epoxide. Notice that in every case, the nucleophile has ended up at the benzylic secondary position over the position that's simply secondary. Okay, the alternative way to open epoxide is through acid-catalyzed epoxide ring opening. All right. So let's look at some examples of or let's look at the general equation. All right, so here we're going to treat the nucleophile with H plus in the presence of nucleophile. We notice that nucleophiles do react with H plus, so a lot of times we're going to have the nucleophile already attached to H, and we're going to add an H plus catalyst. Okay, so how does this reaction go? Well, this reaction proceeds through protonation of the epoxide, and now the nucleophile tends to add to the more substituted position, okay, over the less substituted position. We're going to see that this is a case where we have very high regioselectivity. This is tertiary. That position is secondary. Okay, how do we explain what's going on here? Okay, so down at the bottom we kind of have this explanation. So let's look at it. It really involves this intermediate right here. So when this is treated with methanol sulfuric acid, this is our product. Okay, sorry, I'm at the edge of the writing tablet. All right, so the mechanism, what it seems to do is blending the concepts of SN2 and SN1 type reactivity. It seems like as far as the regiochemistry goes, it looks like an SN1 reaction, but as far as the stereochemistry goes, it looks like an SN2 reaction. We're inverting the stereochemistry, but we're attacking the more substituted position. All right, so what happens here is that our protonated epoxide is in equilibrium with the tertiary carbocation, and there's a high percentage of this present at equilibrium. If you average all the structures at equilibrium, you come up with a structure like this, where most of the positive charge is still at oxygen, but there's a lot more positive charge here, and minimal partial positive charge character at that carbon. All right, so we're seeing it attack the tertiary position because there's a high degree of carbocation character in this reaction. This is really only goes with really high regiochemistry when you have an especially stable carbocation. In this latter case, where we're just competing a primary side with a secondary side, we see that there's very little regiochemistry at all. But recognize that if it was purely a nucleophilic opening, it would go completely at the primary carbon, but clearly there's some of this business that we see down here where there's some sort of carbocation character developing, but it's not developing to the extent that it is in the top one. So unless you're forming a really stable carbocation, it's really hard to predict what you're going to get. We'll just say that the regiochemistry is not going to be nearly as selective as if you had done a nucleophilic epoxide ring opening. Okay, long before you came to this chapter, most of us had heard the word epoxy or epoxide. And so if you look at epoxide glue, and I just downloaded this picture of an epoxide glue. What you see is two tubes. I don't know who's blue and who's clear, but we see call this a hardener in the second tube, and we'll call this one the resin. Okay, so the glue is not any kind of glue at all until these two are mixed. So in the resin tube, we have an epoxide. And the epoxide group, there's actually two epoxide groups in this resin tube. Okay? And in the other tube is a compound that has two nucleophilic sites, in this case an amine. And when these are mixed together, they basically form a long chain polymer derived from the epoxide ring opening. So what's happening here is the nitrogen lone pair is coming along, opening the epoxide that way, and you're ending up with this structure down here. Okay, let's say you don't like the two tubes and you'd like to buy your epoxy glue pre-mixed. Well, it wouldn't work. All you'd have is just a big blob of a hard solid. Okay, So the epoxy glue is actually very strong because it's held together purely by covalent bonds, and it's especially good for porous things. Many of you probably have seen the demonstration. I think I saw it in a commercial many years ago where somebody breaks a baseball bat, then they glue it together with epoxy glue, then they deliberately break the bat again, and it breaks in a different place. Okay, so for like a porous system like wood, epoxy is really an excellent choice. Basically, it sinks into the wood fibers before it actually finishes the polymerization, and you have this nice blob of hardness connecting your what was two separate pieces together. Okay. All right. Let's look at how epoxides can be used in synthesis very cleverly. All right. So we know from a previous discussion how to get a syn or a cis-1,2-diol, and that's by doing a syn addition of syn dihydroxylation. And of course, the reagent of choice here is osmium tetraoxide with a catalyst, so you don't have to use stoichiometric amounts of osmium, which is a very expensive and very toxic substance. Okay, we know how to make syn products very easily, but what if we want anti-products? Well, what you do is you just perform your epoxidation reaction in the presence of an acidic system. What will happen here is that this peroxyformic acid aqueous formic acid mixture generates the epoxide, and under these acidic conditions you get the epoxide ring opening. And remember that this is a meso compound, so it really doesn't have any stereochemistry. But let's just have it attack from the bottom. Okay. We're protonating it. It attacks from the bottom. And we set up the trans relationship. Sorry, I screwed up. I made the enantiomer. Okay, let's make the same compound. All right. Okay, so we're actually going to make a racemic mixture of those two compounds right there. And because the epoxide ring opening, regardless of whether you use nucleophilic epoxide ring opening or acidic or acid-catalyzed epoxide ring opening, you still get anti-addition. Remember, it only affects the regiochemistry. It doesn't affect the stereochemistry. Okay, let's take a stroll down memory lane. Which of these is meso? This one, of course, is meso because it has a plane of symmetry here. And this one is a chiral molecule that could exist as a pair of enantiomers because there's no symmetry plane in that molecule right there. Okay, all right, so let's predict the products of these acid-catalyzed epoxide ring openings. They may not really, or actually, no, these are not necessarily acid-catalyzed ring openings. Let's just look at these. The word then we're going to find is a very important word here, telling us how we do these reactions. All right, so in the top reaction, methanol is present, is the nucleophile, and we're doing this in the presence of sulfuric acid. Therefore, this is an acid-catalyzed ring opening. Okay. If we look at this, the two positions, we have this one secondary and benzylic. This is just secondary. Benzylic generates a stable carbocation, relatively stable carbocation, we'll say, not stable enough to isolate, but kind of like tertiary. So we would predict that we would get that compound with a very high degree of regioselectivity. All right, so the important thing here to note is that the acid is coming along later. Of course, you could not have ethyl Grignard in the presence of H3O+. All you would do is make ethane from the direct reaction of ethyl Grignard with the acid. We're not adding the acid until after the epoxide ring opening has occurred. All right, so this is a nucleophilic epoxide ring opening. All right, and here we're just looking for the best SN2 reaction, and that's going to be occurring at the primary system. All right, and that's the product we would expect. Here's our ethyl group. It doesn't really look ethyl-like when it's just a chain like that, but recognize that we did add 2 carbons when we opened it. Okay, here we also see the word then. This means that the acid is present after the sodium cyanide. Of course, we would want it this way, right? We don't want to breathe hydrogen cyanide. Okay, so this is also a nucleophilic epoxide ring opening. All right, primary there, tertiary here. Primary is the better SN2 substrate, and that's what we're going to make right there. Okay, so I think this is where I'm going to end up in the video. There's going to be one more video on ethers, emphasizing thioethers and some more advanced synthesis problems. We'll begin with that one right there. Okay? All right, so we'll stop the video right here.